Let's optimize the function f of x, y, z equals x times y times z, subject to the constraint 2x plus 3y plus z is equal to 6. For this, we're going to use a method of Lagrange multipliers. So we're going to take the partial, or rather the gradient of f, and set it equal to lambda times the gradient of g, our constraint. So starting off with the partial with respect to x, I'm going to set that equal to lambda times partial with respect to x of g, and then I'm going to do that for y and z. So the partial of f with respect to x is yz, the partial of f with respect to y is xz, and the partial of f with respect to z is xy. And then we're going to multiply that by lambda. And then this one, you can define g of xyz to just be the same thing, except we'll just bring the 6 over. And then take the derivative with respect to x is 2, with respect to y is 3, with respect to z is 1. So we have these three equations, and then the constraint is 2x plus 3y plus z is equal to 6. Notice that on the right side we have lambda times a constant. So we can solve for lambda for all of these guys. That's yz over 2, xz over 3, and then obviously this is just xy. So now we can set these all equal to each other, since they're all equal to lambda. Yz over 2 is equal to xz over 3 is equal to xy. Okay, so starting, let's look at the first two. Yz over 2 equals xz over 3. I can cancel out the z because I'm assuming here that z is not 0. Actually, I'm going to assume x, y, and z are not 0. And the reason is because if x, y, and z are 0, this whole thing becomes 0. That's not going to be the maximum or the minimum. The maximum is going to be greater than 0. Like I could put x, y, and z to be 1, 1, 1, and that's going to be bigger than if we were to put 0. So, and then similarly with 0 is not going to be the minimum because I could put some negative value for x, y, or z. So that it makes this work, and I get a negative value for f. Okay, so then if I'm just looking at the first two here, I can cancel out the z's, and then I can either solve for x or y. It doesn't really matter, but I'm just going to solve for x because I rather work with 3/2 than 2/3. So x will just equal 3/2 y. So now everything is going to be in terms of y. The next thing is to solve for z. So let's look at this second equation here. So xz over 3 equals xy. I can cancel out the x's because I'm saying that it doesn't equal 0. And then solving for z is equal to 3y. So now I have x and z in terms of y. I can plug it into my constraint. The constraint is 2x plus 3y plus z is equal to 6. X we said is 3/2 y. Y is just y, so we'll leave that alone. And then z is 3y. Now the 2's are going to cancel. I have 3y plus 3y plus 3y equals 6. That's 9y equals 6. Dividing by 9. We get 2/3. So y is 2/3. Now I can plug in back into solve for x and z. We said x is equal to 3/2 y, but replace y with 2/3 to get that x is equal to 1. And then for z, we said z is 3y, but we said y is equal to 2/3, so z is equal to 2. So the critical point here is going to be x is equal to 1, y is equal to 2/3, and z is equal to 2. If we substitute these values into f of x, y, z, which remember, it was x times y times z. That turns into 1 times 2/3 times 2, which is equal to 4/3. So therefore, the maximum value of f of x, y, z, subject to the constraint 2x plus 3y plus z is equal to 6, is going to be 4/3. And that is our final answer.